All right, the primary topic of this next mini lecture is going to be the electron dot symbols, also known as Lewis. We could call these Lewis electron dot diagrams, as mentioned in your books. And I do like to mention Lewis briefly, just because a lot of the people we've talked about here and up to this point in the book have been people who have been in the 19th century, early 20th century. We haven't mentioned many Americans, and it's always fun to talk about, people from different locations. We've talked about Germans in the book, we've talked about Russians, we've talked about Englishmen. Well, here's an American who actually did his work from, well, he was alive from 1875 to 1946. He was the Dean of Chemistry at UC Berkeley. This was Gilbert Norton Lewis. Anyways, enough of the history. So the definitions we need to review for this are the valence electrons. So to begin with, we need to define valence electrons. These are considered the outermost electrons, or we could call these kind of surface electrons on an atom. These are the only, usually considered the only electrons available for either ionization or any sort of bond formation. And what these are is these are the electrons located in the S subshell and P, if there are ones there, P subshell of the highest N value associated with S and P. We generally don't look at any D or F subshell electrons. We just concern ourselves with the electrons that are in the highest S and P orbitals. Okay, so very briefly, when we look at electron configurations, then, for example, when we were talking about cobalt, we'll go back here, looking at cobalt, the valence electrons of cobalt are in only the 4s shell. So cobalt has 2 valence electrons. Okay. If you were to look at, let's see, back here with sulfur, sulfur has, as you can see, 3s and 3p are the highest subshells of S and P. So we look at that, look at the electrons. You've got 2 in the S subshell plus the 4 in the P subshell, giving us 6 valence electrons on sulfur. Now, that's important because on electron dot symbols, you only show the valence electrons. Okay. So with this, then we can look at a couple of things. For example, cobalt would look like cobalt and then just 2 electrons. If we were talking about sulfur, we would go 1, 2, 3, 4, and then we start doubling up, pairing these up, 1, 2. Okay, remember, electrons don't like to pair up until there's no space left, and we fill, in general, if we have some element X, we pretend that there's a orbital on each side. Okay, we just pretend that there's an orbital on each side and fill accordingly. So it would go something like 1, 2, 3, 4, 5, 6, 7, or 8, depending on the number of electrons we have. Let's look at a couple of other examples for these, and then we will end this topic here. Looking at the periodic table, for example, bromine. So if you find bromine, it's in the halogen family. Bromine has 7 electrons. So we go 1, 2, 3, 4, 5, 6, 7. If we look at potassium, potassium is in group 1, so it has 1 valence electron, like so. If we look at who else? Silicon. Silicon has 1, 2, 3, 4. So it's got 4 electrons. So 1, 2, 3, 4 valence electrons. Now, if you're wondering how I'm figuring this out so quickly, let us look at something on the periodic table, and then we will end this lecture here. So if this is our periodic table, then remember we're looking at the primary blocks as our source of valence electrons. Then if the element is located in group 1, it's going to have 1 valence electron. So this would be here 1 valence electron. If it's located in group 2, it's going to be 2 valence electrons. The transition elements are very wonky, very difficult. So we generally say don't try to predict. The rough rule of thumb is people sometimes assume 2, but the transition elements are weird. Back to the main group blocks, this would be 3 valence electrons, and then we've got 4, 5, 6, and 7, and finally 8 valence electrons. Okay. Now that brings us to one other thing, the octet rule. The octet rule, as you will read about in your book or have read about in your book, it generally says that an atom is most stable when its valence shell is full of 8 electrons, hence the octet rule, the rule of 8. Okay. Noble gases are classic examples of this. Noble gases are an octet, as you can see on the periodic table. If you look back at our periodic table here, you can see that we've got all octets associated with those noble gases. So they are an octet. They are highly unreactive. There we go. That is the end of this mini lecture. Thank you for your time.